Okay, so let's start with a known net reaction like this one here. So this is NO2 gas, reacts with carbon monoxide gas, produces these two species over here. This is the net reaction. This has nothing to do with the mechanism. It tells us nothing about how the reaction will actually proceed at the molecular scale. There's nothing about this that tells us the molecularity. So let's look at the elementary steps that comprise this. So it turns out it occurs through two distinct steps. So the first elementary step and the second elementary step. And you should pause the video and convince yourself that if you were to add up all the reactants, you would yield these two reactants. And if you added up all the products, you would yield these two after things cancel. Okay, so I've explicitly drawn in or crossed off the species that are redundant on both sides of the reactant. So we have NO2 on the left, NO2 on the right. I can cross those out. Those are intermediates because they're present on both sides, but there's no net change. Same is true for the NO3 species. So how do we relate the actual rate law of the net reaction, which is the thing you actually measure in the lab, to the elementary steps in the mechanism itself? Well, remember the rate law for a full cumulative net reaction like the one given at the top cannot be implicitly determined simply by how it's written. It has to be experimentally determined. We use the method of initial rates to do that. And so let's say that we do that, and what we yield is a rate law in the form of what is written here. So rate is equal to K NO2. That's bimolecular, meaning this is a second order reaction in NO2. That's another way to say this. So this reaction is second order in NO2, but it is not dependent in any way on CO. Let's also assume we have a little bit more information about these elementary steps. Let's say that there's two steps, of course, and the first step is really slow, meaning its rate constant, we'll just call that K1 since it's the first step, is slow, and the second step is really fast, and we have that with its own rate constant K2 since this is a separate individual elementary reaction step. So how does this information relate back to what we experimentally see about the full net reaction? Well, a nice intuitive way to think about this is that the thing that you measure experimentally overall without any knowledge of these individual steps, of course, is going to be the one that is determined by the slowest overall step. If you think about this intuitively and you have two separate steps that are occurring, the first of which is super slow, the second is really fast, what's going to happen is that these two products sort of trickle out really slowly. You don't get very much of them very fast, but the moment they end up in that reaction beaker, they're going to get chewed up by the second step, which is much faster. So what you're going to observe experimentally is simply that slowest step. You're not really going to get much out of that second step. And so your experimental rate law is going to largely mimic whichever the slowest step is. And we sometimes call this the rate determining step. Sometimes people will call this the rate limiting step. A nice analogy for thinking about why that's the case is just imagine each of these steps as a funnel that's stacked on top of each other. So the first step would be the first funnel, and the second step would be the second funnel, which is receiving the outlet of the first. So if we just pour some sort of fluid, we'll just make this some red fluid into the top funnel. If that's a really slow step, that's like having a really narrow-necked funnel that you add material to, but it sort of pools up because it drains so slowly. But if that drains into a really wide spouted funnel down below, then none of that's going to pool up. It's going to go directly through. And so what you eventually observe, in the end, the rate at which these droplets come through both funnels is essentially limited by the slowest funnel. It's no different in the rate of these elementary steps in how they contribute to the overall observed reaction rate or the rate law that we experimentally determine. So finally, this should make some sense because our experimental rate law, we said, was of second order in NO2. That's what that shows. And if we look at our slow step here, the first step, we see NO2 plus NO2. And so if we were to look at just the elementary step and write a rate law for that step alone, we would write out rate is equal to K1 NO2 NO2 which is the same as K1NO2 second order. And that is identical to what we observe experimentally.